on an average about 12 breaths per minute. This is what most of us do. It turns out this is not the best we can do. Okay, just by slightly decreasing that, let's say 12 breaths per minute, let's make it 8 breaths per minute, or the sweet spot for most people seems to be at 6 breaths per minute. Just by slowing down the respiration rate, it turns out you can do wonders to your body. Why it is the case, how it happens, some of the things will, of course, the point of this whole quiz is that, okay, why, what, and all that. Physiologically favorable best shooting position. I'm showing a picture from biathlon. Okay, so this involves skiing and rifle shooting, but there is a standing position, shooting from a prone position, from a sitting position, from a kneeling position. What is being shown is a shooting from a prone position. Which of the four do you think is most suitable for shooting? And there is a reason to actually ask this here. Physiologically favorable shooting position. Notice, yes, the reason to actually talk about this is physiology matters in many, many aspects. Outside of hospitals, from sports, right? For example, when do you know what is a good position to take a shoot? You can actually have physiologically sound answers for this. You're most steady at prone position. Your stability, body stability, is best at prone position. Not just that. Your respiration is most efficient at prone position. You're most calmed down at prone position. That's when your muscular coordination works best. You're more balanced. Stability is good. You're also more calm and relaxed. You can best take the shot. Your aim is best then. That is why prone position shooting is one of the easiest physiologically favorable positions. I have 16 questions. Okay, so this is the first. Let's go to the next question. So we have been, pick all that apply. You've already seen this. See, in life, in homeostasis, extremes are not good. Middle ground, sweet spot, Goldilocks, right? That is always a good thing, okay? Too slow, there is no sufficient oxygen supply. Too fast, there is no sufficient carbon dioxide, right? There is hyperventilation. Again, too fast, too slow is not good, certainly not good. Sweet spot is somewhere in the middle. What we typically do is we kind of like very shallow, okay? Idea is it can be made efficient just by slowing things down. Notice normal breathing is typically shallow. The tidal volumes are too small. It's inefficient. It's very incorrect. But compared to normal breathing, slower breathing. Normal breathing approximately 12 breaths per minute. Slower breathing depends on person to person, amount of practice and training, right? But typically around 6 breaths per minute with reasonable practice is really efficient. Okay, great. Okay, the leaderboard, there is a temporary change in the leaderboard, but let's proceed and see what happens. Yeah, we already had a discussion on this using a PowerPoint slide or a PDF. That didn't work out, which is why I kind of decided I wanted it to be more interactive. I didn't want it to be a podcast. I didn't want it to be a monologue. I already mentioned that, right? So that is the reason why we are doing the same thing, but in a game-based format. I have added as many fun elements as possible, but right, some of the things that we discuss are at the boundary of the science. Okay, idea is this is, there is a lot happening in biomedical engineering, physiological engineering, right? There is a lot we can do about healthcare outside of hospitals, and actually there is a lot of biomedical applications outside of healthcare, for example, in sports and all that, right? And I consider this as a forum where we can have this conversation. Some of the things that we discussed are somewhat advanced, but I will try to make it as approachable, accessible as possible. We have made this is kind of part 2 of this, video where we deconstructed physiological side and consider all different aspects of breathing, mechanics of breathing, different parameters involved and all of that, right? Okay. The disclaimer is missing, but that's fine. Notice what we learned is that some, deliberate breathing practice for 5 minutes a day or something like that brings down your respiratory rate outside of the practice window. Seems to have longer term significance, right? We mentioned breathing is somewhat efficient, when you do it slow, during physiological sigh and all that. That we explained, but we are going to go deeper into the thing today. Okay. So we prescribed Surya Namaskaram, right? Hey, whatever is happening in physiological sigh, same thing happens in Surya Namaskar. But Surya Namaskaram is something that you cannot do everywhere. You are writing an exam, suddenly all of a sudden you cannot do Surya Namaskaram. This is the specialty about breathing. You can do that anywhere and everywhere. And once you learn to calm down yourself using your breath, any situation, ideally, if you put that to use, you can calm yourself down. That's the idea. And the reason to have this conversation is this. I already mentioned this, right? Imagine a bicycle with a one-sided handle. Another analogy is, right? You know how to climb a tree, but you don't know how to get down, right? Unclimb a tree. That's a very poor state to be in. So making a change isn't sufficient. We need to know when something is good, when something is bad, right? We have this analogy from, our epic. We have Abhimanyu, right? He knew how to enter this Chakravyuha, but he didn't know how to exit. That's a very dangerous situation to be in. And as far as physiology goes, quantification is very, very hard, which is why we typically resort to empirical methods and clinical trials, right? But still, there are many aspects that can be mechanistically explained. And today's objective will discuss what makes slow breathing really good for the body. Most of the aspects that we can think of seems to improve just by breathing slowly. Okay. And so extremes are not good. Normal breathing is shallow, it's not good. But if you slightly decrease, why is it good? Okay. When can it potentially turn dangerous? We need to know the mechanisms and why it happens, right? If something has a potential to make so much improvement, it also has a potential to make changes in the other way around. We need to know how things are working. We need to know the underlying mechanism, and it's not as clear cut and as objective. But still, what I have is a collection of objective questions for you. Okay, so let's continue with the question that I have for you next. Moderately slow breathing. What do you mean by moderately slow breathing? Around 6 beats per minute. Okay, this is roughly 0.1 hertz. This is typically efficient in terms of, I think we have seen this question. Interestingly, any aspect that you consider, with respect to the heart, with respect to the respiratory system, with lungs and all that, with respect to the nervous system, brain and sympathetic, parasympathetic nervous system, autonomic nervous system, most of the aspects, right? Most of the systems. Slow breathing involves diaphragmatic control. It also involves, I have 2 minutes for you, alveolar recruitment, roughly the number and amount of alveoli that participate in gas exchange. More alveoli participate, more gas exchange, more oxygen supply happens. Capillary air-blood interface. Reduced alveolar dead space, there is a part of volume of alveoli that doesn't take part in respiration, that is dead space. That is not good. So just by breathing slowly, you reduce that dead space. That's not the only dead space, because all these tubes and all that doesn't play a role in gas exchange. All of that is referred to as physiological dead space, anatomical dead space. They also reduced. So they don't increase. So this is incorrect. And of course, the tidal volume increase, right? Amount of oxygen, gas exchange, difference between this inspiration and expiration respiratory system. It's inspiration, expiration, volume difference in respiration. That also increases. So there is more gas exchange, there is more oxygen supply. This is from the respiratory side. Great. So far, so good. I feel all of you are on the same stage. Great. With a shake of 4. 4 players just hit answer shake of 4. We have 12 more questions. Pick parameters affected by slow breathing. I have HRV, heart rate variability. So beat to beat length, right, for a heartbeat. Not all heartbeats are of the same length. Change in their length, right? One beat is slightly longer, one beat is slightly lower. HRV quantifies that. Respiratory sinus arrhythmia. Heart rate changes with your during inspiration and expiration. That is referred to as respiratory sinus arrhythmia. Vagal tone. How good is your vagus nerve? Vagal activity. That is referred to as vagal tone. Okay. Does it affect the vagus nerve? Interestingly, it affects all of the above. Variation in RR interval. Some of you know that this is associated with sympathetic parasympathetic balance. Respiratory sinus arrhythmia. This is a kind of a measure of how synergistically your lungs and hearts are coordinating this or orchestrating this dance called respiration. Right? How well they are orchestrating that with each other. RSA is a measure of that. Vagal tone, how good is your signal conduction, and specifically vagus nerve is, right, parasympathetic. So that has certain connotations, and for now, it affects all of this. Okay, so yes, R is currently leading. Tree has actually highest streak of answer of 5. That's also interesting. Best time to shoot in archery is typically near end of inspiration, expiration, end of inspiration, beginning of expiration, end of expiration. So true or false? Oh, most of you got this correct, right? Interesting. So best time to shoot an archery is not typically near end of inspiration. So what is it? Actually, end of expiration. Why that is the case? We'll get to that in a moment. So most of you got this. I think some of you might have been, if your speed was good, I think some of you might score slightly higher. True or false? Normal physiology. HR increases during expiration. This is also actually related to why you should not take it at the end of inspiration, take the shot. You should shoot. Rather, you should do it at the near the end of expiration. Okay, few more seconds. I told you, respiratory sinus are your heart rate is not a constant. During inspiration, typically it is higher. During expiration, it's lower. Heart and lungs are trying to work synergistically. Why that is the case, I'll explain in a moment. But right now, notice heart rate decreases during expiration. You're more calm down as you're expiring. You're best calm down at the end of expiration. That is the best time to take a shot, okay? Your muscular control, your aim and all that is best when you're most calm down, when you're most relaxed. If you're tensed, you're jittery and all that, right? Your muscular control is not good. That's not the time to shoot. Best time to take a shoot is to actually when you're most calm down. That happens during end of expiration when your heart rate, has decreased the most. Okay, why that happens? Of course, that's a objective of today's discussion. We will do that. So there is this parameter called heart rate variability. Should this parameter be high? Should it be low? That is a question kind of posed in this one. I'm showing a figure here. This is canine data. Which gives me some opportunity to explain this heart rate variability. During physiological stress, when your body is stressed, HRV increase or decrease. If your body is stressed, happens. Stress is always not a bad thing. Stress is where you learn and adapt. Your body learns and adapt. But chronic stress that is associated with inefficiencies in physiology and that is associated with poor prognosis or bad expectation from the brain or the mind, that is not good in the long term. Something is stressing you, you find it as a challenge with a growth mindset, that typically improves you. An obstacle, you see it, right away, I'm not able to process, that constricts you further. Okay? So physiological stress as such is not a bad thing. What your body does to it, how you react to that depends, but typically physiological stress, things are most efficient when you're relaxed, when you're calmed down. Okay? And when you're relaxed, your heart rate variability, this beat to beat variation, right? Let's look at this media. Notice, for example, here, this is canine data, okay? RR interval is 440 milliseconds. Here, the RR interval is 850 milliseconds. So, from beat to beat, the interval length changes. Heart rate variability is a measure of this change, okay? And typically, what is likely happening is, the canine being experimented is inspiring here where the heart rate is increasing. It's expiring here where the heart rate is decreasing. Likely. Okay? We don't have respiratory rate data, but that is what is happening. Notice heart rate is roughly around, let's say, 130. From that, it actually goes to 80. The average is somewhere over here, very deceptive, right? From 130 to 85, 90, right? It kind of varying. This variation is likely due to respiration, inspiration, expiration. That is one thing. And the amount of this variation tells you how good this lungs and heart are working in tandem. So higher this variation, the better it is, typically. So when you are calmed down, when you are not stressed, unwantedly stressed, okay, HRV should increase. Increased HRV is a sign of health, typically. Okay. So that is why we have this question. One of you seems to have got it correct, hopefully not by chance, okay? But we have many more questions to give. Who is? Yes, sir. Okay, great. cardiovascular parameters. Now, we looked at some respiratory parameters. Now, these are cardiovascular parameters, heart and blood vessels affected during normal inspiration. Venous return, intrathoracic pressure, cardiac output, perhaps all of the above. What it is, I'll quickly explain. But most of you should have guessed this correct. Just by the process of inspiration, you are not only, breathing, slow breathing, you're not only affecting your lungs, you're also affecting your heart. In which way? Notice this heart is in this space between the two lungs, right? As you inspire and expire, the volume around the heart changes. The atrium being specifically tender, it's sensitive to the pressure, this transmural or transthoracic pressure in this cavity, thoracic cavity. And that pressure changes during expiration. So, respiration can have a significant effect on the atrial pressures. Okay, if your atrial pressures are affected, the amount of blood that gets gathered in the right atrium, venous return through the veins that get affected. If more blood returns, more blood gets pumped, cardiac output gets affected, and this parameter, intrathoracic pressure, right? So the pressure in this cavity, that gets affected. So this pressure is one mechanism through which this respiration kind of interacts with the respiratory system, interacts with the heart system. Okay, and a pointer here. So if you're breathing slowly, all these parameters should change. They should change in a way it improves things. Status quo. That's a hint. Okay, for questions that show up down there. Someone has a streak of 3. Also, I think I made these questions today afternoon, so no one could have known this question. Venous return. Pulmonary capillary pressures, cardiac output are typically not affected during normal expiration. We saw it gets affected during inspiration. So they get affected during expiration. So as it turns out, as a thoracic pressure, right, thoracic pressure changes, it not only affects atrial pressure and all that, venous return and all that, it also affects the lungs, pressure that the lung capillaries feel, that also changes, okay, which is why I put that, and that is correct. In fact, it so happens that whether you are inspiring or expiring, these parameters get affected, and typically in a positive way, if you are breathing slowly, okay? Nothing is spared. All of the systems here get affected, okay? Now, someone has a streak of 4, okay, fine. During slow breathing, roughly around 6 breaths per minute, typically, now I have questions on some of the parameters. How should these parameters change? I gave you lots of hints. Blood pressure pulse better synchronizes with heart rate, decreases venous return. Okay, that happens. You can kind of quickly make a couple of detections and conclusions. Diaphragmatic excursion is relatively suboptimal. Diaphragmatic excursion is like this amount of movement of diaphragm, let's say, in simple terms. Okay, amount of diaphragm usage in respiration, that is suboptimal. So all of them change, but should they increase, decrease? That's a question. Be careful. Hey, great. So it actually increases venous return, in turn increases cardiac output. Great. Diaphragm is used optimally, more optimally, not suboptimally. Great. So notice what is happening here as your lungs and heart, they start working synergistically. Your heart and blood vessels, they start working synergistically in tandem, just by breathing slowly. Okay. This is what I refer here as, the blood pressure variations get modulated. 1, 2 extremes are avoided. Not just that, the entire vasculature tries to help the heart. Notice the vasculature is not passive. It has smooth muscle cells, right? It has actually capabilities to drive some blood, control pressure. That starts working, helping your heart. So it synchronizes with heart rate. So the vascular system starts working in tandem with the heart. That happens just by breathing slowly. Some of you got this. Venous return decreases, cardiac output decreases, right? Typically heart rate increases and all that. You have less oxygen supply. It's not great. SSN was initially leading. I don't know. Actually, most of you, I don't know who is who. SSN, who is thought, but fine, let's proceed. Someone seems to be getting a nice lead. Correct. Typical sequence of baroreflex. There is a system in place that controls pressure variations. There is a negative feedback loop, homeostatic mechanism, to keep pressure at homeostatic values or within homeostatic range. Gets too high, brings it back. That is known as baroreflex, baroreceptor reflex or baroreflex. How does signal propagate in the system? There should be a sensor. Something should take it to the central nervous system, should get it back to the, let's say, what is capable of taking some action. Typically a muscle, but there are a few other things that can take actions, corrective actions. Again, most of you guess this correct, notice. So we start with the sensor. Afferent nerves take signal to the central nervous system. Here they typically go to the medulla oblongata. From there, the vagus nerve is where the correction, this efferent nerve is where the correction comes from, right? Now, vagus nerve can actually change the pressure. They can also start having other changes, like can change respiratory rate, heart rate. I don't know if there is a question down the line, but vagus nerve, being a parasympathetic nerve, tries to calm things down. So when vagus nerve is activated, typically your respiratory rate decreases, heart rate decreases. Okay, fine. So this pressure correction system is there in place. You also need to account for that. What does slow breathing do to that is a different question. Okay, we'll get to that. Again, who is this Asena? I don't know. We'll come to that, okay? Slow breathing, around 6 beats per minute, typically. HRV, heart rate variability. Some of you might want to know. VPR, ventilation perfusion ratio. Improves, this is baroreflex, okay? It's not baro. I just explained what baroreflex is. The whole point of it, the previous question is to introduce you to the term. This is ventilation perfusion ratio. We have seen this in class. Balance between ventilation and blood supply, air supply and blood supply. Very, very simple terms. And should HRV increase or decrease? There is one more question that actually gave you some hints and answers. Increasing heart rate variability is a measure of calming down. Yes, slow breathing calms you down, typically increases HRV. The balance between respiration and perfusion, the air supply and blood supply at the lung capillaries, ventilation and perfusion, that are actually more balanced, okay? That actually improves. In a way, this gets efficient. And, this is expected. Data is suggesting that, but, this is very plausibly. There isn't like real good sound evidence to conclusively say that. That's why I have added plausibly. So that's correct. It improves this baroreceptor system. Okay, baroreflex pressure correction system. It does improve it. So it makes it more sensitive for pressure changes. Okay, brings back control more reliably, in other words. So all of the above. Yes, sir has a streak with 7 correct answers in a row. Great. Actually, I think, just 2 more questions. Slow breathing, typically, should it increase or decrease? I give you sufficient time, be careful. 70 more seconds. Decreases vagal activity or tone. ANS, autonomic nervous system, shifts towards parasympathetic dominance. Certainly optimizes sympathovagal balance. All of the above. I said vagus is parasympathetic, so sympathetic parasympathetic balance, I suppose, is what is being referred to. Still have time, think about it and answer. See, all of the above is very tempting, right? Fortunately, this is very tempting. Decreases vagal activity. Sometime, a few questions back I mentioned, it improves vagal tone or vagus nerve activity. Vagus nerve is a good nerve. It calms you down. If its activity increases, if its tone increases, that is good, right? Again, in simple terms, doesn't decrease it. It actually increases vagal activity or vagus tone, okay? That is incorrect. Also notice there is a difference between saying autonomic nervous system shifts, from a parasympathetic mode, dominant mode to sympathetic dominant mode, it shifts to a parasympathetic dominance mode. That is, there is a fight or flight response, sympathetic, calming down response, parasympathetic. Calming down response starts dominating. That does happen. But this is different from making sure these two systems are in balance. That's a very different thing. One starts dominating, right? That is different from concluding the balance between the two is better, right? And it also notice the certainly is a very, very problematic word in terms of typically in biology, right? So it doesn't certainly optimize it. This is again hypothesized, but we don't have data or evidence to certainly make that conclusion. Okay, what we know is that this calming down, this parasympathetic system starts dominating more. That we certainly know. I think we have one more last question. Okay, we'll wind up in a couple of minutes from now. Okay, so scorecard, pick actions where breathing rate and phase, that is expiration, inspiration, possibly matter. We started out with archery shooting, prone position, and all that. What is again? This is a statue showing someone shooting an archery. Right? Where do you think this matters? Does it matter? Does breathing matter during public speaking? How you breathe? Does it matter if it starts mattering when you shoot? If it starts mattering when you read a question, when you answer the question, when you click an answer, do those details matter? While you are listening, learning, participating in this course, how you breathe, does it matter? Again, I have added some words to make it more reasonable. Okay. So likely during public speaking, even if you're giving a simple seminar, right, a simple talk, any of that project presentation, if you're kind of anxious, the typical advice is start breathing, take a deep breath, right? Calm down, right? Because notice just by the act of breathing deep, we are decreasing respiratory rate. With that, pretty much all aspects of cardiorespiratory, cardiovascular, autonomic nervous system, we are improving it, okay? Moderately slowing down respiration. This is why this common suggestion actually seems to have a strong physiological backing, okay? Seems to matter during public speaking, likely. There is also sufficient evidence for this, but while listening and learning, memorizing something, plausibly this matters. Plausibly. Speculatively, again, we don't have data here, that's why it's a speculation. Okay? It matters during shooting, it matters when you read it, how you read it, right? When you answer it, when this thing starts mattering. But I don't think there is data to make a conclusion there, so that's why I've made it speculation. So right now, in fact, the conclusion is all of the above. Okay? So one of the best things that you could do is to just breathe slowly. Okay, so we have SSN, we have Dinesh, and we have yes or right. Great. Okay, you just 5 minutes or something like that. I just take some feedback while you wind up. But the point is this: mindfulness. If you are mindful about your breathing, does your respiratory rate decrease? In fact, one of the papers that we discussed, it said that it doesn't seem to at least have an effect outside of the practice window, right? 5-minute practice window. Outside of that, the respiratory rate doesn't seem to significantly change, right? But if you're mindful specifically to relax, mindful about relaxing, about calming down, about breathing slowly, right? That seems to be a different scenario. That is one reason why being mindful can have a possibly good effect. It boils down to breathing slowly, breathing deeply, breathing better, right? So this again, physiological side we explained, right? Alveolar recruitment, distension, diaphragmatic excursion, all of these are kind of improved, right? So it works. The real question here is, so if slow breathing is, let's say slower breathing is good, why doesn't the body do that? By default, why doesn't that happen? Body should have recognized, no, it's better, should have started doing that, no? Instead of 12 breaths per minute, why isn't your default mode doing why is it not doing 6 breaths per minute? Why is it doing 12 breaths per minute? Don't you think your physiology recognize, hey, there is a better optimal solution there? We should move towards that. What do you think is happening, right? Why is that not happening? We don't have clear answers. Mechanistic answers. We can do empirical studies. We don't have clear mechanistic answer. I'll give sort of a reasonable answer. Okay, that is one thing. And the real problem with this studies is, we are doing clinical trials and empirical studies is, it's hard to quantify, certainly say what will happen. Okay, fortunately, this is one system where we can actually make so many calls about the trends. The trend should be, the change should be this way, change should be this way. There aren't actually many systems where we can make that call on a typical change. It's a very, very, very peculiar system, in sort of kind of a unique system. So there is a lot to learn from it. Point number one. Okay, and not from a mechanism side, not a lot is known. There is a lot to be explored. Okay, this is quite potential. This is quite powerful. Slow breathing can improve things in a lot of fronts. But again, as I said, if it's so potential, it can also be dangerous if used incorrectly, right? So the demarcation has not been clearly done. How slow is good, right? Or, you slow at this breaths per minute. For the long term, it's really good for your body. That is not very clearly established. And some of the things that I discussed, each of the questions typically is the research paper. Okay. This is knowledge acquired over a couple of decades, is what we learned in this session. One thing. Okay. And what is likely happening in physiology is two things certainly needs to happen. One is any change that we are talking about should make the system more efficient. Slower breathing is making how lungs and heart work in tandem more efficient, right? Efficiency should increase. Okay. If that alone happens, that doesn't suffice. Okay. The body doesn't starts taking that as a default mode. One more thing, at least one more thing needs to happen. That is your mind, your brain, conscious, unconscious, subconscious, right? Again, in simple terms, that system needs to recognize the change is more efficient. Whatever, slower breathing is driving the system towards, is making the system more efficient. That needs to be recognized by the brain. That doesn't always happen. Quick example, eating sugar feels good, right? But does it make the system more efficient, improve the system? No, not necessarily, right? So feeling good, what the brain thinks and what happens at the system level, body level, are two different things. Typically, when these two go hand in hand, system efficiency increases, brain's opinion on that, and brain's opinion involves conscious, unconscious, subconscious parts, right? That should kind of synchronize with what is happening. Then the changes in your long-term changes in your body seems to really improve. Okay. This is what is likely happening, and your control here is this conscious part. You should identify what changes are good for your body. You should identify them, and you should acknowledge them. You should put that into practice, and gradually and hopefully that gets passed on to your voluntary, this medulla oblongata regions where you don't have conscious control. Even, that is one place where you don't have conscious control. Even at a genetic level, you don't have conscious control. But hopefully, you have control of the conscious, only at the conscious level. Good things you need to recognize as good, and eventually, your body seems to learn that. Okay. So this is what is happening. So I wanted to get you to this boundary of this. Okay. Now you can start learning, exploring, and putting this to good use. I showed you a couple of examples. Okay. So this is a good place to stop. And where I got you today is not many aspects of that is at the boundary of science. Okay. Who is this SR, by the way? Who is SR? So within this, so the physiological engineer is